There are worlds in our galaxy that have never seen a sunrise. Planets with no star, no warmth, no day. There may be black holes moving silently through the Milky Way, almost impossible to see because they emit no light of their own. And beyond our galaxy, something we still don't understand is accelerating the expansion of the universe. For decades, we have searched for fragments of this hidden cosmos. That is about to change. On August 30th, a Falcon Heavy is scheduled to leave Earth carrying a new eye into space. Its name is Roman, and it was built to see what Hubble never could. For more than 3 decades, Hubble has transformed our understanding of the universe. Then James Webb pushed infrared astronomy deeper into cosmic history. But astronomy has always faced another problem. The universe is enormous. Imagine trying to map an entire continent through a keyhole. You might see extraordinary detail, but only a tiny piece at a time. There are galaxies by the billions, stars exploding and disappearing. There are galaxies by the billions. Stars erupt in brilliant explosions, then slowly fade back into the darkness. Planets passing silently in front of distant suns, and enormous structures stretching across cosmic distances. To understand them, astronomers don't only need to look deeper, they need to see wider, and that is where Roman changes the game. Meet the Nancy Grace Roman Space Telescope, a next-generation observatory built to survey the universe on an extraordinary scale. At the heart of Roman is a primary mirror 2.4 meters across, almost exactly the same diameter as Hubble's. But Roman was designed for a fundamentally different kind of astronomy. Behind that mirror is its wide-field instrument, a 288-megapixel near-infrared camera. Roman will capture Hubble-like sharpness across a field of view at least 100 times larger. But seeing wider isn't the goal, it's what that wider view allows us to find. Across that immense view, Roman will map galaxies and cosmic structure on an unprecedented scale. Instead of slowly assembling tiny pieces of the cosmic puzzle, Roman can begin seeing the picture around them. Same universe, similar exquisite detail, a radically larger window, and instead of slowly assembling tiny pieces of the cosmic puzzle, Roman can begin seeing the picture around them. But Roman's enormous view wasn't built simply to make beautiful panoramas. It was built to investigate something much stranger. Stars, planets, gas, dust, ourselves, all the ordinary matter we know, represent only a small fraction of the cosmic story. Dark matter reveals itself through gravity, shaping galaxies and bending the light that travels through them. Yet we cannot see dark matter directly. We infer its presence from what gravity does around it. Dark energy is stranger still. It is the name we give to whatever appears to be driving the accelerating expansion of the universe. Current measurements suggest it accounts for roughly 68% of the universe's total contents. But giving something a name is not the same as understanding it. We still don't know what dark energy actually is. Roman will map enormous populations of galaxies and measure how cosmic structure and expansion changed through time, and somewhere inside those patterns may be an answer. Across the universe, stars sometimes erupt with enough light to outshine entire galaxies, but one particular kind of explosion became something far more valuable, a cosmic measuring tool. Unlike the death of a massive star, a Type 1a supernova begins with a white dwarf, the compact remnant of a sun-like star, in a binary system. In one possible scenario, the white dwarf pulls material from its companion, gradually gaining mass until it becomes unstable. These explosions have a remarkable property. Their predictable intrinsic brightness allows astronomers to use them as cosmic distance markers. Measure how bright the explosion appears, compare it with how bright it should be, and its distance can be calculated. Observe these explosions at different distances, and you are also looking at different moments in cosmic history. And when astronomers compared their distances with how fast their galaxies were receding, they discovered something astonishing. The expansion of the universe is accelerating. Those observations revealed that the universe wasn't simply expanding, its expansion was accelerating. Roman will push this technique dramatically farther. Its sweeping surveys are expected to reveal tens of thousands of Type 1a supernovae across cosmic history. Each explosion becomes another measurement, another point on the universe's timeline. Together, they could help reveal whether dark energy has remained constant or whether its influence has changed as the universe evolved. Roman won't only photograph the universe, it will repeatedly return to selected regions of the sky, again, and again, and again. Suddenly, the universe stops looking like a collection of frozen photographs. Stars flicker, supernovae appear, objects move. Hundreds of millions of stars lie toward the crowded center of our galaxy. Roman will watch them. And when a planet passes between us and its star, the star dims, just slightly. That tiny shadow can reveal a world. And Roman won't see just a handful of these shadows. NASA expects this survey to reveal more than 100,000 translating planets. But Roman has another trick: gravity itself. When a foreground object passes almost perfectly in front of a distant star, its gravity bends and magnifies the star's light. This is gravitational microlensing. A planet can leave a second smaller signature inside that distortion. Microlensing will reveal more than 1,000 additional exoplanets, particularly worlds farther from their stars than transit surveys usually find. And some may have no star at all, rogue planets, worlds wandering through the galaxy alone. No sunrise, no sunset, just an endless journey through interstellar darkness. But planets aren't the only things hiding in the darkness. Our galaxy may contain an enormous population of stellar mass black holes. An isolated black hole gives us almost nothing to see. No glowing companion, no bright accretion disk, just gravity. And gravity is enough. Roman's microlensing survey is expected to reveal hundreds of stellar mass black holes, along with more than 1,000 neutron stars. Objects that may have been drifting through the Milky Way unseen for millions or billions of years. Roman doesn't need them to shine. It only needs them to bend the light behind them. And then there is Roman's second instrument, the coronagraph. Imagine trying to photograph a firefly beside a searchlight. That's the problem astronomers face when they try to photograph a planet next to its star. So, Roman will attempt something extraordinary: suppress the star's glare. Its coronagraph will demonstrate advanced technologies designed to reveal worlds hidden beside nearby stars. Roman isn't designed to photograph another Earth. Instead, it will demonstrate direct imaging technologies by observing giant worlds, including Jupiter-sized planets around Sun-like stars. The real prize may come later, because technologies proven aboard Roman could help pave the way for future observatories capable of studying worlds increasingly similar to our own. Roman may not find Earth 2.0 this way, but it could help teach the telescope that someday will. Roman isn't replacing James Webb. It doesn't need to. Their strengths are complementary. Roman is built to discover enormous populations across huge regions of sky. Webb can investigate selected targets with extraordinary sensitivity and detail. Roman can reveal where the interesting objects are. Webb can help us understand what some of them are. But Roman creates another problem: too much universe. During its 5-year primary mission, Roman is expected to generate roughly 20 petabytes of observations, 20,000 terabytes, trillions of individual measurements of stars and galaxies. That's hundreds of times the rate at which Hubble has accumulated data. And inside that archive will be more than the objects Roman was specifically designed to find: transients, anomalies, strange gravitational lenses, unexpected populations, perhaps things nobody thought to search for. Because some of astronomy's greatest discoveries weren't answers to existing questions. They created entirely new questions. For centuries, astronomy advanced by seeing farther. Galileo expanded the human eye. Hubble escaped the blur of Earth's atmosphere. Webb opened new windows into infrared cosmic history. Roman adds something different: scale, the ability to combine exquisite detail with an enormous panoramic view. Over its lifetime, Roman could measure light from more than 1 billion galaxies. Think about that, 1 billion galaxies, each containing millions or billions of stars. Somewhere inside that ocean of information may be a planet unlike anything we've seen, a black hole we never knew was there, a clue to the nature of dark matter, evidence that changes what we think dark energy is, or perhaps something nobody thought to look for. On August 30th, 2026, if the current launch schedule holds, a Falcon Heavy will rise from Launch Complex 39A at Kennedy Space Center. Inside will be a telescope named for Nancy Grace Roman, NASA's first chief of astronomy. and the woman remembered as the mother of Hubble. The spacecraft will begin its journey away from Earth. But what really begins that morning is a much larger journey, because for the first time, humanity will have an observatory capable of combining Hubble-like sharpness with a view of the infrared universe at an extraordinary scale. We know what Roman was built to find: dark energy, hidden worlds, invisible stellar remnants, billions of galaxies. What we don't know is what it will find that nobody expected, and perhaps that's the discovery worth waiting for.